Welcome to this Quantum Security and Defense presentation, Building Quantum AI at Scale, and thank you for being a valued member of our community.
Dr Sonika Johri is founder and CEO of Coherent Computing, a company focused on building software platforms to enable users to take advantage of the rapidly expanding capabilities of quantum hardware. As a principal researcher at IonQ, she led a team working on quantum applications R&D for clients including Hyundai, Fidelity Center for Applied Technology, GE Research, Goldman Sachs, Airbus, and Thomson Machinery. She has authored 40-plus publications, recently focusing on cutting-edge quantum algorithm demonstrations in the areas of generative and discriminative machine learning, quantum chemistry, optimization, and condensed matter physics across a variety of quantum hardware platforms, as well as developing frameworks for quantum benchmarking. She has a PhD in theoretical condensed matter physics from Princeton University.
You would need fewer qubits than you would need the equivalent amount of classical hardware. And then, of course, there's some very unique things that can happen when you combine quantum models with other quantum transforms, right? Like, when you train a quantum model, you don't just have the model by itself. You can use certain quantum transformations, like the inverse of it, or you can combine it with a quantum Fourier transform or Hamiltonian simulation, and all kinds of magic can emerge from that. And we're just beginning to understand all of that. So there's lots of exciting reasons to study and try and build quantum AI at scale. And then at the other end of the spectrum, we also know that quantum hardware is very steadily scaling. So there are many different quantum hardware backends that are being built commercially, and these span, whether they're transpons based on superconducting technology, or spin qubits or ion qubits. They're all, there are several different companies that have. Oh, can you still see my screen? Yeah, so there are several different companies that are building these hardware platforms, and they've all put out their different roadmaps, right? Very ambitious, and I don't expect that all of these roadmaps will pan out as as advertised, but still one can't deny that all the different quantum hardware backends are steadily scaling. However, this presents a dilemma to anyone who's building applications on these hardware, because it turns out that quantum programming at the moment requires you to know at a very detailed level the idiosyncrasies of each hardware platform. And then to add to that, every time new hardware comes out, it causes some of the software programs that have been developed to become obsolete. So this is not a good situation. To kind of address this kind of messy situation at the hardware level, at Coherent Computing, we are building what you can think of as the Android for quantum computers. So we call it Red Cedar, which is a quantum operating system that is designed to be scalable. So it should scale to thousands of qubits. It should be modular. So it has, by modularity, I mean that it's composed of these different building blocks, right? So at the bottom, you have hardware-specific layers, and at the top, you have hardware-independent layers. And the bottom of the quantum OS, or quantum computing software stack, it interfaces with different quantum hardware APIs. And on the top of that, you have these hardware-aware quantum circuits. And on top of this quantum OS, you have these APIs that integrate into different domain-specific workflows, which are in turn built on top of quantum application libraries, which are built on top of this quantum programming framework. Which right now we're calling quantum structures, which in turn can be compiled down to quantum circuits. And this modular structure also allows for the OS to be portable between different hardware frameworks, because you can keep the higher level programming layers as they are, even if you switch out the lower level hardware backends. And of course, it allows it to be user-friendly, right? So if you are, for instance, a genomics expert, then you don't really want to know about, how to program qubits based on ion traps, right? You want a lot of routines that will quickly allow you to implement a solution that is relevant for your domain area. And this kind of approach allows you to do exactly that.
Watch the full presentation, plus lectures from over 70 more global experts, plus take training, and join the quantum innovation community. Simply search Quantum Security Defense for more information.